Good afternoon, everyone. So for some years, I had a dream of the spectral gap of a random walk being related in the inverse way to the spectral gap of another process on the graph, like the easing model. And and then I saw this remarkable paper that Daniel wrote with Lionel, Levine, and John Pike, which realizes this kind of dream in the setting of the Sandpile. So I'm very happy we'll hear details about this from Daniel Jersey, please.
Thank you, Yuval, for the invitation. So this is joint work with Lionel Levine at Cornell and John Pike, who is just finishing a postdoc at Cornell and will be starting at Bridgewater State University in the fall. And it's that archive paper. OK, so I know there are some people here who are experts on everything to do with sandpiles and other people who may not know very much about it. So for the beginning of the talk, I'm going to briefly introduce what the sandpile group is and what the model is, and then I'll talk about what the random walk is that we have defined, and then the results that we're able to prove about it. So you start off with a graph. I'm going to have it be a simple, undirected, finite connected graph. The simple part is not that important, but it is necessary for it to be undirected in order for some of these things to work. And the number of vertices will be n. And the sandpile group is a way of defining an abelian group from this graph. So you might think, OK, how do I take a graph and create a group? And it turns out that a number of different people have had different perspectives on this, but they all ended up with the same group in the end. And so they gave it many different names. And so it was invented by statistical physicists because they wanted to study something called self-organized criticality. It was invented by combinatorialists because they invented a game called chip firing. Even an economist decided to invent a version of this. And it all comes down to the same thing in the end. And then there's also a connection with kind of discrete arithmetic geometry, which I don't know anything about, but they have their own way of thinking about this. And then more recently, there's something called Sandpile PDE that was invented that has to do with the scaling limit. And there are connections with computability theory. You can kind of make a version of the halting problem that has to do with this. Anyway, it's a nice enough model that it has interesting connections with a varied list of other fields of math. So what I'm going to do is to define this random walk and talk about the mixing properties of the walk. So here's the description of the model. We have a finite graph. Here's a graph. And you choose one vertex to designate as the sink. That one. And a chip configuration on the graph assigns some non-negative integer number of chips to each of the non-sink vertices. So I could, for instance, have 3 chips here, 1 chip here, and 3 chips there. And you say that a vertex is stable if the number of chips at the vertex is lower than the degree. And it's unstable if it's equal to the degree or higher. And so a toppling operation is allowed if the stack is unstable. And what happens then is that the stack of chips topples over, and 1 chip gets sent to each of the neighbors. So if this vertex topples, then the 3 will get replaced by 0. And then this will become 4. And this will become 2. And then the chip that went to the sink just disappears. So then maybe this one can topple. So this one, it now has 4 chips, so it can topple twice if it wants, or once. Let's only topple it once. So then you have 2 here, and this becomes to 3, and this becomes to 1. And now this one is still unstable, and this one is also unstable. But you can see that if you just keep on toppling, then eventually enough chips will fall into the sink that you wind up with a stable configuration. And the so-called abelian property of this model is that it doesn't matter in which order you do the topplings. I could do this one next or that one next, and so forth. At the end, when it stabilizes, it'll stabilize to one unique configuration. And it's also true along the way that the number of times that each vertex toppled does not depend on what order you chose to do the topplings. So this was proved by Dar back in, I think, 1990 from the statistical physics point of view. OK, so that means that if you start from any configuration, then you can define its stabilization, which is down at the bottom of that slide, which is uniquely defined. OK, so I let capital S be the set of all the stable configurations. And it's not a group, but it has an operation, which is pointwise addition followed by stabilization. And the operation is associative because of the abelian property, that if you first add a to 1 and a to 2, but then a to 3, or the other way around, you always wind up with the same stabilization at the end. So I define a subset of the stable configurations called the recurrent configurations, which are the ones which are always reachable. So if I imagine here that I have, for instance, one chip here and 0 and 0. And then you kind of continue to add chips, at some point you're never going to be able to get back to this configuration. Just because if you have some stack of chips here, some there, and some there, then it's not going to be possible to topple so many chips into the sink that you recover this. So even though this one is stable, it's not recurrent. And there is a test that you can do to see whether a configuration is recurrent or not. The definition is just as given that if it's always reachable from any stable configuration, it's recurrent. So one configuration which is always recurrent is the one where the number of chips at every vertex is equal to the degree minus 1. So if you put 2 here, and 1 there, that's, each vertex is filled to capacity. So that one is definitely always reachable. And then anything which is reachable from that is also recurrent. And so it turns out that if you just focus on the recurrent states, that forms a group. And so you might wonder, what about inverses? Well, it turns out that those exist. You might also wonder, what about the identity? Because the identity in the stable configurations is just all zeros. That's OK. But it turns out that there is an identity configuration which is recurrent. And that on big graphs has a beautiful structure, which I'll give a picture later in this talk. OK, so the graph Laplacian matrix has a lot to do with the structure of this group and gives another way of describing it. So there's n vertices, remember, including the sink. So the Laplacian matrix is an n by n matrix. On the diagonal, you put the degree of the vertex. And then on the off diagonal, you have either 0 if in entry ij, if vertices I and j are not adjacent, and 1 if they are adjacent. And if there's multiple edges, then you can have negative numbers larger than 1. So it's a symmetric matrix, and the sum of every row and every column is 0 because you have the degree and then minus 1 for each edge on the other entries. OK, so notation, I'll let z0n be the set of all column vectors where the entries sum to 0, r0n, the same thing for real numbers. And if I have a chip configuration like this, I can list some ordering of the vertices, say 1, 2, 3, 4, and then I associate v1, v2, v3, v4, and then I associate with this configuration the column vector 0, 0, 1, minus 1. So I just list the number of chips at every vertex. And then at the sink, I put a negative number of chips so that the total sum is 0. And of course, there's a unique way to do that. So in this way, any chip configuration can be identified as an element of Z0n. And once you do this, it turns out that the Sandpile group is isomorphic to Z0n mod a lattice of full rank. So that is Z0n is contained in R0n, which is an n-1 dimensional space. And I would look at that delta Zn as the integer span of the columns of the Laplacian matrix. That's also an n-1 dimensional lattice. So this is a finite group. And I look at it as configurations mod topplings. Like if I were to topple this vertex without worrying about that there aren't enough chips, that means I take 3 from here and I put them 1, 2, and there. And what that does is it subtracts the third column of the Laplacian matrix from this vector. You go -3, +1, +1, +1, and that's one of the columns of the Laplacian matrix. So this is a way of writing the Sandpile group kind of explicitly so that it's clear that the group doesn't depend on which vertex you chose to be the sink, because this description is independent of which sink vertex you chose. And it also follows from this that the order of the group is the number of spanning trees, because the theorem says that the principal minor of the Laplacian matrix is the number of spanning trees. OK, so this slide doesn't have anything to do with the rest of my talk. It's just things about the Sandpile group. So this is a very cool result of Melanie Wood. If you take an Erdős-Rényi graph with fixed probability p that does not depend on n, the number of vertices, and you send n to infinity, what is the group? Is it a cyclic group, for instance? And she conjectures that it is cyclic with probability 0.79. And this is the Riemann zeta function. So it's the product of the inverse values of the Riemann zeta function at odd numbers. And she has a good reason for making this conjecture. And indeed, the upper bound is proved, and the lower bound is conjectured to be true. So you can write this down, but actually finding out what the group is a very difficult question. And then this picture, if you've gone by one of the posters on the second floor, it has this exact one. This is a picture of what the identity element of the Sandpile group looks like when the graph is a large square grid where the boundary is identified as the sink. And then you pick the recurrent configuration, which acts as the identity, and it's color-coded because it's a square grid. Each site has 0, 1, 2, or 3 chips at it, so it's colored one of those 4 colors. And it's this beautiful fractal structure on the outside, and it has this solid green square. And then it was proved by Levine, Pegden, and Smart that there is this kind of variant of Apollonian circle packing that they call Apollonian triangulations. I don't think that they proved that the Apollonian triangulations appear in the identity element, but it's almost certainly true that it has to do with this. So all kinds of cool structure. Now I'll define my Markov chain, which is the actual subject of the talk. And this is very simple. You have a configuration, and you just choose one of the vertices uniformly at random, and you add a chip, and then stabilize. So that's one step in the Markov chain. And you can see that even if you start at a configuration like this, eventually you will land in the recurrent states and stay there forever. Then at that point, it's a random walk on the Sandpile group. So I will denote by P the transition matrix for the chain, and I want to know how fast it converges to the stationary distribution, which is uniform because it's a random walk on a group. And the I'll be talking about total variation distance and also L2 distance. And total variation distance is given by this. It's kind of if you take the worst possible set where the measure that you have differs from the measure that you want, then what's the difference in the measures that are assigned to that set? And of course, it doesn't depend on the starting configuration because it's a transitive walk. OK, so the mixing time with parameter epsilon is the first time that the variation distance drops below epsilon. And this is not a reversible random walk. It would be reversible if you, at every stage, you could either add a chip or take away a chip. But you're only adding chips, so it's not reversible. But it is a normal matrix. That is, it commutes with the time reversal. And so all of the bounds that you would expect to be true for reversible chains are also true in this case if you look at, say, the absolute spectral gap or the absolute relaxation time. So that's what this slide is about. So this formula that the total variation distance is bounded above by the sum of powers of eigenvalues, absolute values of eigenvalues because they're complex.
Can you say in the beginning it's not reversible, but you can still
But it's normal. Yes, it commutes with its time reversal, which is just, in this case, the matrix commutes with its transpose. Oh, and then this thing is actually kind of cool, that the moduli of the eigenvalues of the random walk are independent of the choice that you made for the sinc vertex. And this is true in the way that I've defined it. But for instance, if you were going to make a continuous time version of this Markov chain, then the mixing time would depend on the sinc that you chose. It could be off by a factor of n, depending on which sinc you choose. But for the discrete time version, where it chooses also, sometimes you drop a chip at the sinc with probability 1 over n, which does nothing, then this quantity, which is the L2 distance from stationarity, actually is independent of the choice of sinc. So that can be proved.
Something I didn't understand. The mixing time in discrete or continuous time don't differ much.
So what happens is that when you can have a situation where it's very nearly periodic.
If you do the lazy chain, the eigenvalues are just going to be...
Yeah, but this one isn't very lazy. It's only lazy with 1 over n factor.
But you said all the eigenvalues don't depend on the choice of sinc.
The absolute values of the eigenvalues don't depend. The eigenvalues themselves do.
Okay.
But what happens is that when you change the sinc, then each eigenvalue does a rotation. But the eigenvalues do different rotations, but their absolute values stay the same.
So if you average them with 1, then the absolute values change.
Yes. Yes. Mm-hmm. OK, so based on that, I want to look at the absolute spectral gap, which is the smallest value of 1 minus absolute value of lambda for a non-trivial eigenvalue, and the absolute relaxation time, which is 1 over the gap. And then this is the standard upper and lower bounds for mixing time in terms of relaxation time. And they work here just as if the Markov chain were reversible. So the lower bound is the relaxation time. The upper bound is the relaxation time times the log of the order of the group. And the order of the group is the number of spanning trees of the graph, which can be pretty large. OK, so a couple of examples. These are really the main 2 examples that I'll return to through the talk, because they represent kind of 2 extremes. So you can have a cycle. And let's put the sinc up here. So it's an n cycle, and the number of spanning trees is n, because you just remove a single edge and you get a tree. And also the number of generators of the random walk is n, because you can choose any one of these n vertices to drop the chip at. So it's the group is Z mod n, as it turns out. And in fact, what happens is that you jump directly to the uniform distribution after a single step because the n generators all produce different elements. So the random walk mixes in a single step perfectly. And the other extreme is when you have a complete graph. So here's my sink, and I'll label special vertices V and W. And I'll keep track of the number of chips at V minus the number of chips at W as the Markov chain proceeds. OK, so let's say that you add a chip at V, then that number will increase by 1. And if you add a chip at W, the number will decrease by 1. And if you add a chip anyplace else, then maybe it causes some very complicated sequence of topplings, but it has the same effect on V that it has on W, because all of the other vertices can't distinguish between V and W. And so the only thing that can happen is, let's say it starts out that V has more chips than W. They get added chips, and then eventually V topples, but W doesn't. And when that happens, V sends away n minus 1 chips, and one of them goes to W, so the difference mod n does not change. And so if this y quantity only changes when you drop a chip at V where it increases by 1, or at W where it decreases by 1, and then if you just keep track of that statistic, it's performing a simple random walk on Z mod n with lots of laziness. It moves 1 to the left or 1 to the right with probability 1 over n, otherwise it stays. And the amount of time that it takes for that to mix is n cubed. So definitely the overall Sandpile chain has to mix in time at least n cubed. And in fact, it's n cubed log n because you have it not just for these two vertices, VW, but any pair of vertices. And so based on that, you can get a lower bound of n cubed log n. And this thing there is actually an eigenfunction for the Sandpile chain. That if you take eta of V minus eta of W and take a root of unity to that power, then it turns out that exact function is an eigenfunction. The eigenvalue is 1 minus constant over n cubed. And then you have many of these, and that gets you a mixing time at least n cubed log n. And then that is the right answer. That's the right mixing time for this random walk. OK, so 2 lessons come from this. First of all, there seems to be, at least in these 2 cases, an inverse relationship, like Yuval was saying in his introduction, between the simple random walk and this chain. Here, simple random walk takes n squared, but the Sandpile chain mixes instantly. Here, the simple random walk mixes in constant time or instantly with the right laziness, and the Sandpile chain takes n cubed log n. And the second thing is that we can probably make progress by looking at the eigenfunctions. If we can compute those, then those will allow us to find out information about the spectral gap and the mixing time. And so, OK, random walks on groups, there's a great theory for this. And if it's a non-abelian group, you have to look at the representations. It's an abelian group, so all the irreducible representations are one-dimensional. So all you need to look at are the characters, that is, the homomorphisms from the group to the unit circle in the complex plane. OK, so this is the general theorem for eigenfunctions of random walks on abelian groups. You have a random walk on an abelian group, and mu is the measure driving the walk. Then no matter what mu is, the eigenfunctions are the same. They are these characters. But then the eigenvalues depend on the measure which is driving, according to this formula, which is reasonably simple. So that's, I guess, due to Diaconus in the 80s, probably. OK, so, well, I mean, yeah, the proof is about 1 line. But you had to come up with the idea. Anyway. OK, so we had this way of describing the group as a lattice mod another lattice. And so if you just do some diagram chasing, say, OK, what are the homomorphisms from this thing to the unit circle, then the right answer is to take the dual of this lattice mod the dual of that lattice. And when you do that, you wind up with this thing. The one on top is you take the pseudo-inverse of the Laplacian matrix times z0n, and then you mod out by something which is not important. That is, what it is isn't important, but the point is that the dual group kind of naturally has this lattice structure. And so the first main contribution, I think, of our paper is a more concrete way of looking at the eigenfunctions. That one back there is also going to be very useful, but the concrete approach is built out of these things which we call multiplicative harmonic functions. So an example of a multiplicative harmonic function is, say, on this graph, I'll have the function value be 1 here, 1, 1. At v is omega, and at w it's omega inverse, where omega is a fifth root of unity. And the property is that it's kind of a multiplicative version of the harmonic property. When you take the value here to the power of the degree, it has to be equal to the product of the values of the neighbors. So here, omega to the fourth equals omega inverse, because omega is a fifth root of unity. So that's a multiplicative harmonic function. And the theorem is that, first of all, these form a group by pointwise multiplication. This preserves the harmonic property. And the characters are determined by these things, and the character group is isomorphic to the group of these multiplicative harmonic functions. And the correspondence is a reasonably simple formula. If you have a chip configuration with, say, 1, 2, 3, 4, and 5 chips, then the value of the function is omega to the third times omega inverse to the fifth. And then the even better thing is that there's a very simple formula for the eigenvalue based on the values of the multiplicative harmonic function. It's simply the average. So in this case, it's 1 plus 1 plus 1 plus omega inverse over 5. And if you imagine a big complete graph, you can put ones everywhere except for a single omega and omega inverse. And that's how you get 1 minus constant over n cubed for that eigenvalue. OK, so there's two different ways of describing the dual group. That means there has to be a correspondence between them. And so I'm going to describe that now. So suppose that you have this h function, and you write h equals e to the 2 pi I times g. So in this case, the blue one is h, and the green one would be g. So g would be 0, 0, 0, 1/5, and 4/5. And so the property that the g has is that it's harmonic mod z. That 1/5 times 4 equals 0 plus 0 plus 0 plus 4/5. That's actually true. But if you have, for instance, 0 times 4, then it's the sum of the other ones plus minus an integer. So another way of looking at that is that when you take the graph Laplacian and apply it to G, you get a vector whose all coordinates are integers. And then if you subtract off the mean so that the overall sum of the coordinates is 0, that's that G bar over there, then you get your dual lattice vector. And of course, you made arbitrary choice for G. I could have added any integer value to these. And when you do that, you get an answer for G bar, which is off by an element of this Wn. So that's the correspondence. So I will call this pseudo-inverse Laplacian lattice to be the dual lattice. And so this means that the eigenfunctions and the eigenvalues have a lattice structure, and that will let us prove things about the spectral gap and the mixing time. OK, so this is the way that the lengths of vectors in the lattice relate to the eigenvalues. So you can see there's this 8 and the 2 pi squared. So there's up to a constant factor, the gap between 1 and the modulus of the eigenvalue is determined by its Euclidean length in the dual lattice. If you pick the shortest vector in the dual lattice that corresponds to that multiplicative harmonic function. So for this one, I guess you would take this, and then its sum is 1, so you have to subtract a fifth from all the coordinates. And then you have to massage it so that it's the shortest possible one. Once you have done that, then the squared length divided by n up to a constant is the gap from 1 of the eigenvalue. This is not that hard to prove. The reason that it's off by constant has to do with the approximation of cosine, like 1 minus cosine x by x squared over 2, which is very good near the origin, but once you get kind of far off, it's off by a constant. And so what that means is that the absolute spectral gap of the Markov chain is determined by the shortest vector in the dual lattice, with an exception, which is that sometimes the shortest vector in the dual lattice is actually one of the ones that corresponds to the trivial eigenvalue. It can happen. So once you have gotten rid of all of those, then the shortest remaining vector in the dual lattice determines the spectral gap of the Sandpile chain. OK, so these are the bounds that we proved on the spectral gap. So we have the maximum degree of the graph, and then beta is the spectral gap of the graph Laplacian matrix. So the lower bound, upper bound for the spectral gap of the Sandpile chain. And if you apply it to the cycle, then this upper bound is completely terrible. The lower bound, neither bound is correct, but the upper bound is really awful. So the degree is 2, right? So the lower bound is 1 over n, and the beta is 1 over n squared. So actually, this right-hand side is n cubed. So we just proved that the spectral gap of a Markov chain is at most n cubed. OK, so it's actually equal to 1. It's neither 1 over n nor bigger than 1. Of course, it can't be bigger than 1. On the other hand, for the complete graph, this is correct on both sides. The left side is n cubed. The right side is also n cubed. And in fact, whenever the graph is an expander, either a regular expander or nearly regular, say the overall ratio of the max degree to the min degree is bounded by a universal constant or something like that, then the left and the right side of this bound have the same order. So we have the correct order of the spectral gap for the Sandpile chain. And this is the inverse relationship, kind of, or at least the best that we've been able to prove for the inverse relationship, because for the expander, that's where the simple random walk mixes the fastest. And that's also where this upper bound is the smallest. So that means that the spectral gap of the Sandpile chain is as small as it can be up to constants. OK, so the next slide will have proof of these two. Actually, neither one of them is all that hard once you have built up the theory of the lattices. Yes. Of the graph Laplacian. So that means that if the degree is d and it's an expander, then beta is proportional to d.
For a complete graph, you have a large spectral gap.
Okay. So I guess I think of expander as like when you normalize the Laplacian, then the spectral gap is constant. But when you don't normalize it and it's regular, the spectral gap is proportional to the degree.
For the complete graph, what is beta?
Beta is d, or something, a constant multiple of d. Or n, yes. I guess d is n.
Not the normalized Laplacian.
That's right. It's not the normalized Laplacian. It's the graph Laplacian. Mm-hmm. Yeah, this seemed to be the most natural thing that was true, the relationship in terms of the graph Laplacian. So, I mean, if it's regular, then it doesn't matter which one you take. If it's not regular, then I think this is the relationship that's true. And if you were going to try to figure out if there's a relationship with the normalized Laplacian, there might not be a nice one. OK, so the lower bound, this is basically saying that because it's a lattice, it can't have points which are right next to the origin. So we imagine, let's say that we have a multiplicative harmonic function, and the multiplicative harmonic function takes values on the unit circle, right, like the blue values there. And the situation that would lead to an eigenvalue very close to 1 in absolute value is if all of the values of the function were in a very narrow arc of the circle. Yeah?
Sorry, this is maybe backtracking a little
No, go
bit,
ahead.
but so when you were defining multiplicative harmonic functions, did you require that they always take values on the unit circle? Or is that just
Yeah, but if you allow them to take values in C minus 0, and you require that the sink be normalized to be on the unit circle, then they all are on the unit circle by a maximum principal thing. So that's not a restrictive assumption. OK, I guess the sink has to have value 1, but pretend that it didn't. That would be OK. Imagine that all of the values of this thing were here. So that means that the average value would be very close to the unit circle. And I want to claim that it cannot happen unless they actually are all at one point, which would correspond to a constant function. So when you take g, which is the angles, then g has to be kind of integer harmonic. And so you take the Laplacian and you get a number which is composed of the differences between angles. And if the angles are too close together, then you get a sum which has to be less than 1. But it's an integer, so therefore it's 0. So that means something like this is not possible if the interval is too small. And if you figure out what bound that gives you, it gives you exactly the lower bound here. So for the upper bound, remember the spectral gap is determined by the length of the shortest vector in the dual lattice. So the generators for the dual lattice are these EI, EJs, or standard basis vectors. You have to do EI minus EJ because it has to be coordinates summing to 0. But in fact, all of these are short vectors if you have an upper bound on the operator norm of the inverse, the pseudo-inverse of the Laplacian. So the operator norm, the L2 operator norm of the pseudo-inverse is equal to 1 over the spectral gap of the graph Laplacian. And so when you run through that, you get this bound, a constant over beta squared. And that's the same 1 over beta squared that comes here. So I'm not, in this part, I'm not glossing over any hidden details. That really is all that you have to do.
You see why you're not glossing over?
Well, no, there aren't any details to gloss over. I mean, I guess what I'm trying to say is that we were very surprised to find this inverse relationship. But then it turns out that the proof is relatively short.
Upper bound.
OK, so what this says is if I take any basis vector, then I multiply it by the pseudo-inverse. Now I have a vector in the dual lattice, and it's a short vector. And so, in fact, I have a full basis of short vectors. So at least one of them is a short vector, which isn't one of the bad ones that secretly corresponds to the trivial eigenvalue. And then, since the vector is short, we know from here that the spectral gap is bounded above by that length squared over n. OK, they're hidden in the previous slide. OK, so that's what we can say about the spectral gap. So how about the mixing time? So upper bound for the relaxation time is d squared n. And the size of the group could be as large as d to the n. What it actually is usually some constant to the n, where the constant is less than d, but say like d over 2 or something like that. So the log of this is close to n log d in practice. And so the standard bound in terms of relaxation time is d squared n times n log d. And it turns out that we can improve that to d squared n times log n, which is better, right? This gives n cubed log n for the complete graph. And the way that we do that is by using this thing called the smoothing parameter, which was invented by Michiancho and Regev, who are computer scientists studying lattice-based cryptography. But it's a lattice invariant. And it just happened to be exactly what we need. And they already proved the things that we need to use. So that was very nice. So of course, you want to use all the eigenvalues and not just the spectral gap. All of my bounds are L2 bounds. So I'm not going to do any kind of delicate stuff relating to L1 versus L2. The sum of the powers of the non-trivial eigenvalues you can show is bounded above by this thing. So x is dual lattice vectors. What this actually is, each lambda corresponds to a particular vector in the dual lattice. You could say here's your lattice, and then you have a fundamental domain for your lattice. And in this case, I guess there are 6 eigenvalues. But so the middle sum is bounded above by a sum involving these 6 points. But that, in turn, is bounded above by the sum over all the non-zero points in the dual lattice, which is not that bad because these are the closest ones, and it's e to the minus norm squared. So you're not adding that much when you do this. And then it turns out that this is the quantity, it's kind of Gaussian sum of squares of lengths of vectors in a lattice that was considered by Michiancho and Regev. So what they say, all right, suppose you have any lattice in Rk, you let lambda star be the dual lattice, which is defined in this usual way. And you take a Gaussian, so let's say I'll tile Rk with copies of the fundamental domain of the lattice. You pick a central point, and then you pick a Gaussian, which is centered at that point and has covariance matrix to be a scalar multiple of the identity. So it's this kind of a blob. And then you take the quotient by the lattice so that now you have a density on the fundamental domain. And the question is, how close is that to uniform on the fundamental domain? Clearly, if the Gaussian has very small variance, it's very far from uniform. But if the variance is large, then it will be close to uniform because the red boxes will be very small compared with the scale of the Gaussian. So it was proved, I think, using Poisson summation that, in fact, the L infinity distance between this quotient density and uniform is exactly this type of Gaussian sum. And then the smoothing parameter is defined to be the amount of variance that you have to take in order for the L infinity distance to be epsilon. C has disappeared. It doesn't matter what value of C you choose, whether you take the centered here or up there. It's translation invariant. It just changes the location where the L infinity thing is achieved. So this thing, when r increases, the distance decreases. You pick the value of r that makes this sum equal to epsilon. That's the epsilon smoothing parameter. And this is exactly the sum that we had in the previous page. And so it says at the bottom, the mixing time of the chain is controlled by the smoothing parameter for the lattice, for the original Laplacian lattice, not the dual lattice. And if you see down here, if this thing was less than 4 epsilon squared, 4 times variation distance squared less than 4 epsilon squared, the variation distance will be less than epsilon. So that's this bottom line here. And then the good news is that there are upper bounds on the smoothing parameter that were proved already by Michanccio and Regev that we can just use. And that allows us to get this upper bound for the Sandpile chain on the complete graph, which actually is an upper bound for the Sandpile chain on any graph with n vertices, but in particular the complete graph. And it says that the mixing time is at most n cubed log n times particular constant, 1 over 4 pi squared. And then if you add constant times n cubed, then it decays exponentially. And then we get a matching lower bound for the complete graph based on the argument that I gave earlier with the omega and omega inverse and all of the different versions of that and different pairs of vertices. So those two together give cutoff for this particular Markov chain, which is nice. And it's probably true that for a few other examples, like complete bipartite graph or something like that, that you could also get cutoff by these methods. But certainly, if the graph is interesting at all, then you'll need to do better for the upper bound. How much time do I have left?
5 minutes.
5 minutes. OK. Well, I have 2 slides, so that should work.
So what is the C of these 5 forces?
Oh, that's just, this is what our complicated numerical computation gave. It's not real. It's just, you do various approximations, and this is what happens. Just like this 35 is not real, and the gap between the 1 and the 35 is also not real. But it does give cutoff with a window of n cubed. OK, so let's say that you take a big square grid or a torus, which is the grid that wraps around on itself. And this is what the physicists cared about to begin with. So what do our methods give? Well, OK, so if you want a lower bound on the mixing time, the best that we can get is a diameter bound, which is n squared order. I guess here, unlike the rest of the talk so far, there are n squared vertices and not n. The upper bound, which comes from the smoothing parameter, is n squared log n. And then just yesterday, I heard that Bob Huff has a proof that the lower bound is also order n squared log n, that he was able to find enough eigenfunctions, short dual lattice vectors, in order to get that matching lower bound up to constants. And we don't know anything about cutoff or anything like that.
The relaxation time is n squared.
Yeah, the relaxation time is n squared. OK, then the last thing, this is a group of physicists in Australia. And what they did computer simulations for a relatively small grid. Group operation, yes. OK, and they found this very strange pattern. They took many runs of the chain, and they had a few statistics that they kept track of, and they followed their convergence toward the stationary value. And this is on a log scale in the y-axis and linear scale in time in the x-axis. And you see that it decreases at a kind of a steep rate, and then it decreases by a slower rate after that point. So they claim this is convergence on 2 time scales. That at the beginning, it has a fast rate of convergence, and then it has a slow rate of convergence. And so we're trying to figure out why that might be. And one theory is that there are kind of 2 groups of eigenvalues. There are the eigenvalues with a gap of n squared, and there are the eigenvalues with a gap of n. And that kind of the 2 clusters of sizes of eigenvalues lead to the 2 slopes of lines in this log plot. But that's just hypothetical. We really have no idea what's the source of this picture. All right, that's it.
What about tori in other dimensions? So,
let's see.
Dimensional torus?
Let's see. So, well, if the dimension is constant, then it should have basically the same upper and lower bounds as 2-dimensional torus. Because if it's bounded degree, then you have, this is number of vertices, so n to the d log n. And then the lower bound, I think, by diameter should also be n to the d. And my guess is that whatever Bob's argument is could probably also be extended to d dimensions, but I don't know what his argument is.
Any other questions or comments?
Yeah.
I just have a quick question. I'm kind of excited about that this has an inverse property of the random walk. Mm-hmm. I'm wondering if those applications that random walk actually doesn't work very well because the convergence is too long. Mm-hmm. Can be applied, let's say, your method, let's say for sampling, uniform sampling, and like that?
I don't think so. I mean, one of the issues is that the group here is very large. Like for the cycle, the group is n, but for a complicated graph, the size of the group is the number of spanning trees. And so even if it mixes fast, so to speak, the mixing time is still going to be at least comparable to the number of spanning trees, which is a very large number. And so if you want to sample uniformly from the underlying graph, then that should be a much easier problem than trying to build this much bigger thing with spanning trees.
Why do you think number of spanning trees?
Oh, so...
I mean, you see in your example, right?
Oh, you're right. That was just wrong statement. OK. Thank you for correcting me.
But still, it's sampling from a very different space.
Yeah. Yeah.
Still exciting.
Mm-hmm.
Any other comments or questions? No, let's thank Daniel again.